So we're going to look at these parts, these electronic components, the things that go into a typical circuit board. And they can basically be put into two groups, general parts and semiconductors. Semiconductors are often the things that are made out of that black stuff called silicon. This stuff you might see like with these chips, and we're going to talk about each of these. Not always made out of that. That's one of the materials that they use. And they semi-conduct. They kind of sort of conduct. They allow us, why are we talking while I'm talking? Turn around and do what you're supposed to do. And spit out whatever's in your mouth too. They kind of sort of conduct. Put another way, they allow us to control the flow and do some pretty cool things with electricity. And that's what it's all about. Changing the electricity, doing something with it, because just electricity flowing through a wire is pretty much useless. And the reason we're covering this today, there are a few questions on this on the test on Thursday. But the main reason we're covering this is because when you get your circuits, you will see almost all of these parts found in your circuits. And I want you to understand what they do. Not just, be a good little trained monkey and put it in the board and solder it, but actually have some sense of what they do. If you can recognize these parts, and you recognize the symbol that goes with each one, that'll go a long way to helping you being able to take a schematic, something like this, and turn it into reality. And I'm going to tell you more about that in the days to come. But you need to be able to read a recipe to make a circuit. But you also need to know what flour, sugar, and salt are. They're all powders or granules, and they're all white. They look a lot alike, but they're quite different, and they do different things in a recipe. Likewise, each of these do a different job. So you're going to learn what they do and the symbol, the schematic symbol that goes with each one. So you're leaving space to write that definition of what they do and the symbol that goes with each one. Here are all the schematic symbols that you're going to be able to identify. And you will have to do several of these for the test. When we take the lab test, you'll have to know them all. Okay, so some of this is for our test on Thursday. Some of it is for the lab test later on. And we're going to go through them pretty much in order as you see them here. As you know, they tried to make the symbols make sense. Head up, Zach. They try to make them make sense. And this picture actually does make some sense. It does kind of look like what it would do. What do you think that part does? What is its job? What does it look like it would do to the electricity?
It's a resistor.
It's a resistor. It looks like something that would slow the flow. It looks like a speed bump. Here you are driving your car down the road that is the wire, and bump, 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 bump. Pretty nasty set of speed bumps there. A resistor slows the flow of current. A resistor slows the flow of current. And that's a very common thing that we need to do in our circuits, is slow things down. Now remember, it's not a conductor and it's not an insulator. Those are opposites. Conductor permits the flow. Insulator resists the flow to the point where it's pretty much stopped. A resistor allows it to flow, but on a limited basis. So they are definitely not the same as insulators. Now, one of the things I want you to get from this today is that not all the parts that you'll encounter will look exactly like the examples I'm going to show you. There are some common examples that I can show you, but you wouldn't be able to know what every single light bulb looked like. If I brought in 50 examples of 50 different light bulbs, there would still be other examples that don't look exactly like those 50. You become accustomed to knowing what to look for. You know that a light bulb has threads around the base where you screw it into the socket. You know that it's got a glass part. It's got a little filament on the inside. And once you know to look for those things, you know what pretty much every light bulb is. You could say that's a light bulb. Well, it's the same thing here. Not all the resistors look the same, but they all have two wires. One coming in, one going out. And usually they're shaped like a cylinder, like you see here. Sometimes they're shaped as big white blocks. In the case of the big white ones, which you won't encounter very often, the resistance, the amount of resistance is written right on it. In the case of the cylinders, how do we know the amount of resistance? The code on the thing. That would be the colored bands tell you that. Okay? So you can look at the colored bands. If you look up on the TV, you'll see what I'm talking about, the colored bands on these. And when we build our circuits, you'll have to identify which resistor is which based on these colored bands. There's actually a resistor color code that we use. So I do want you to add that to your notes, that you can tell the amount of resistance by the colored bands. You can tell the amount of resistance by the colored bands. People that work with circuits a lot will be able to look right at that and tell you how much resistance that has, how many ohms of resistance. I could also take it and hook up a meter on either end and find the resistance that way. Okay? All right, so that's a resistor. Now, if we have that symbol with a little arrow pointing to it, looks a lot like a resistor, but it's called something else. It's called a Zach?
Capacitor?
No. That looks like a resistor to me, but it's a little different. Variable resistor. A variable resistor, also known as a potentiometer. The term you had at the beginning said potentiometer. Sometimes they just write pot for short. A potentiometer is a variable resistor. Now the word variable, I know you guys have heard of it in like algebra. It's the letter used to take the place of something else. It holds the place of something else, of a real number. But you can put in the real number in its place. You can change it. And that's what variable means. It means changing. A variable resistor is one where we can change the amount of resistance. We can control the amount of resistance. And if we control the resistance, we can control the flow. If you think about it, remember our schematic for the crystal radio? What was this part? And what's this part? Coil. And remember how we had it drawn like that? Well, what that indicated is that I can change where that antenna connects to the coil. And by doing that, it's the same as doing what with the radio? Tuning it. By adjusting the length of the coil, where it's connected to the coil, I can tune it in. Well, that's the same thing we're seeing here. And you might notice that this symbol now, instead of showing 2 connections, it shows 1, 2, 3 connections on it. So a variable resistor, or pot, as you see over here on this side or up here or in the corners, they look quite different. But what we're looking for is, number 1, does it have something that can be turned, can be adjusted, like this? Something that can be adjusted. And number 2, does it have 3 connections? Variable resistors will have 3 connections. 1, 2, 3. Okay? They may be big, they may be smaller like this one. Now this one I'm showing here may not look like it has 3 connections, but it does. Because this one and this one are the same. So I've got 1, 2, 3 connections. And you can read right off of these how much resistance. How much is this one? 200,000. That's what the K means. How much is this one? 100,000. Okay, you ignore the B. It says 100,000 ohms. So that means that on this one, if I adjust the knob all the way one direction, I get 0. In the other direction, I get 100,000. And in the middle, I get 50,000. So I can control. I actually have some variable resistors like these in the room that are in plain sight. There's probably at least a dozen. Can you point to any of them? Something that can be turned that adjusts the flow. Sedona? No, well that would be for water. I mean for electricity. What are you pointing at? The little green box over there? Yeah. That's my power supply. Yep, there's a volume control on that, or a intensity control. I have one on the Van de Graaff generator. I have one on my stereo for volume. Patrick has that. I even put one up there on the speaker because I don't like that speaker sometimes. It's too loud for me, so I can turn it down. You see that on any of the other classrooms, chances are I put it in for them. Okay? And I've got a whole bunch back there on that guitar amplifier. All those little volume controls, they are variable resistors or pots, potentiometers, that you can control the amount of resistance. Yes?
Wouldn't that be like a lot better than just a normal resistor?
It's not better. I mean, there are occasions where we just want it to be a fixed amount. We don't need to change the resistance. We need to set it at a certain point and leave it there, like cruise control. And then there are other occasions where we need to give the person with the device control over that. They want it to be loud or not so loud. So no, these are not always better. We also have the kind of variable resistor that you wouldn't see unless you open up the device. They would be inside the case. And these are called trimmer pots. And what they're used for, and you don't need to write that down, what they're used for is to fine-tune the equipment. Let's say it's a DVD player or CD player. That disc has to spin at a certain speed. Maybe the motor makes it go a little too fast or a little too slow. Head up, Matt. So the technician, when they build it, they get in there and they use a little screwdriver and they adjust this one here. This one can also be adjusted. You don't need a screwdriver for it. And they can change the amount of resistance that way. But it's not something that you or I are expected to be messing with. It's inside the box and should be left alone. How much resistance does this one have? 1 million. Okay? And this one is in code, so you're not going to know by looking at this one. You'd have to check up the number. So you can't just go by the size. Okay, this has got more resistance than this one. You have to read off the code. Just like you can't look at these and know based on the size how much resistance. You use the colored bands. This little guy is called a multi-turn pot. And again, you see 1, 2, 3 connections and something that can be adjusted. Those are your clues that you're looking at a variable resistor or pot. So I'll pass these around. You can take a look at them firsthand. Eventually, you're going to have a lab quiz, and I'll have circuit boards laying out on the table, just like we did with the frogs. And you'll have to go around and identify what the parts are. Next one. Actually, both of these are a type of this part. What does this symbol, what does that symbol look like that we've already talked about? Which comes from a battery. This looks like a battery symbol. Remember, battery symbol? But notice that the two electrodes aren't the same length. That means that these two plates, these two electrodes, aren't really different. They're two pieces of metal separated by some other material. It's not a battery. Okay, a battery is an electron pump. It gets electricity to flow, creates the flow. This doesn't create the flow. Instead, it stores a charge. A capacitor stores a charge. And I've shown you two slightly different symbols. This one here goes with this type of capacitor, and this one here goes with these types. Okay? Slightly different symbol. This one here would have a plus sign on it. This one would not. That means that when we're using this type of capacitor, it doesn't matter which way we install it. If we put it in this way or this way, it's still going to work. On this one, it very much matters which way we put it in. If we install it backwards, they have a tendency to blow up. Let me show you what these look like. This gets a little tricky now because, again, they don't all look the same. There are many, many different kinds of capacitors. There are ceramic capacitors. This is called a ceramic disc. Here's another ceramic disc. This is called a mylar capacitor. Looks like a chiclet. So does this one. But they're not always green. They could be blue. They could be brown. But they're still that same kind of shiny plastic material.
Does the color make a difference?
No, it's just the material they use in the manufacture. Sometimes I can tell by the color the type of material that they use, like mylar or tantalum or whatever it may be. But like this, I can tell by that that's ceramic, like a ceramic pot. But those are all capacitors. I know because they tend to be flat, because they have two flat plates close to each other. and they have weird numbers printed on the side. They don't have colored bands, okay, like the resistors. All of these are known as electrolytic capacitors. You don't need to write that down, but what I wanted to share with you is just show you how a little bit of knowledge can go a long way. Occasionally, I have friends or family who give me a stereo and they say, would you take a look at this? It stopped working one day, and I'm just going to have to buy a new one if you can't fix it, because there's not a lot of places that fix electronics anymore. Head up, please. And so I said, sure, I'll take a look at it. Now, guys, I don't know what the heck I'm doing. Okay? I'm not an electrical engineer. I don't know how to go in there and measure and find out what's wrong with a circuit like that. I don't have that kind of skill, but I have some very basic knowledge that can be useful sometimes. And I fixed electronic devices that cost $500 with 30 cents worth of parts because I did this. I pick up the box and I shake it. Ooh, something's rattling around inside. And I get a little grin inside because I know I probably can fix that. I open it up, and what I find is a part like this is in two pieces. The bottom part with the wire sticking out is still on the circuit board. The top part, all of this, the can, is floating around inside there. It's loose. And I know what happened. They either hooked it up to too much voltage. How much can this one handle? 35. Or they hooked it up backwards. Notice that this has a minus sign on one side. Just like you see here. Minus side is this wire closest to it. So I know that this wire is negative and this wire is positive. If you hook it up backwards, they have a tendency to blow up, to pop the top, okay? Well, this thing is designed to store charge. Its ability to store charge is rated in farads. A farad was named after Michael Faraday. And it's abbreviated with an F, a capital F, like you see here. Because farads are very large amounts of storage capacity, most of these are going to be listed in microfarads. This is 1,000 microfarad. Now, do I know all about that? No. I know how to read it off. I know that to look for those two measurements, those two numbers. So what I do then is I take that thing out of their stereo, and then I go into an electronic supply place, and I say to the guy behind the counter, oh yeah, I need a 35 volt, 1,000 microfarad capacitor. Like I know what I'm talking about. And he goes to the back and he brings one out. That'll be 35 cents. And I spring for the 35 cents. And half an hour later, I've soldered in a new one of these, and the thing works fine. Okay? Now, I don't know what I'm doing, but I can read off a label, and I can go buy something that looks just like it and works just the same. So these are used a lot to store charge like you would see in a flash. This one even says photo flash right on it. Look how many volts this one can handle. 330 volts. Fun little trick they used to do in electronics lab is charge it up. Hook it up to an outlet, give it 330 volts, and throw it to someone and say, here, catch. And what happens when they catch it? They get a little shock because they touch the two wires. Okay? Sometimes the wires come out of the same end like they do on this one. That's the negative, that's the positive. And sometimes they come out of opposite ends. I know the arrow is pointing to this one as the negative, so that means this one's the positive. And here you can see on an actual flash on a camera. There's the flash, and there's the capacitor. So, you get the camera ready to take a flash picture. It builds up high voltage from your low voltage battery through a transformer, sends that to a capacitor that holds the charge, and then when you hit the button to take the picture, it sends that charge to the flash, because you need a high voltage flash, high voltage surge of energy to get the flash to go off. Head up, Matt. My capacitors over there are slightly larger than these. So if this is a big capacitor, and it is, imagine how much a charge those can hold. You guys were a big capacitor too. I stored up a charge on you. Not as well as those, but I stored a charge on you. Remember when we built up a charge? Well, for the few of you that weren't too chicken. And then we discharged it. Zach, question?
Yeah, I was going to say, if a capacitor stores the electrons, wouldn't the electrons that get back up when you store too many or something like that?
Exactly, which is why they have a rating, like the number of volts. Okay, pass those around to you. You can take a look at those. All right, so this would be the symbol for that type of capacitor, an electrolytic capacitor. I know it's not going to be one of the flat ones. It's going to be one of the round can-shaped ones. Okay? And those come in different colors too, but they always have two wires, and one of them is going to be labeled negative. And that's the symbol for it. All right, next, we're up to here. You know this one is antenna. Now, everyone knows an antenna for its job of capturing energy, receiving information, but it also can send it. So your cell phone, for instance, the antenna built into your cell phone both sends and receives information, electromagnetic energy. That's what the EM stands for. It can send and receive that. Or we say transmit and receive. Transmitting antennas for the radio stations are often found out on Swan, off of Swan there, or up on Mount Bigelow with the red lights on them. It could be as simple as a hunk of metal stuck up in the air. Or if we want it to be directional so we can focus where we're sending or receiving that information from, we might shape it differently. This type of TV antenna is designed to be pointed. It's designed to pick up signals from this direction and reject the ones from other directions. Because if we get signals we're not trying to get, we call that interference. Yes?
Isn't like satellites point to like the equator?
No. No, there's a certain altitude, elevation too, that above the horizon that the satellites can be found. So many degrees above the horizon. And when you hook up your dish or DirecTV satellite dish, it has a little signal strength thing on the inside, and it will tell you as you're pointing it whether you get it just right on the satellites. Those satellites, unlike the stars which move across the night sky, they are in a fixed position relative to our position here on Earth. So as the Earth rotates, they stay fixed with us over the sky, so you can always get that signal. And whether it's a big dish or a little dish, it's locked into that one signal. Sometimes you'll see these dishes and they'll be pointed not up towards the sky but sideways. Has anyone seen these dishes pointed sideways? Maybe about this big around? Okay. You can have communications, a direct line. You can send a signal out, sky head up please, from one building all the way across town to another building. So there's a direct communication between them. You might see them on like fire stations and places like that. And I'll just tell you a quick little story. I got free cable TV quite a while ago, and it wasn't illegal. And here's how I did it. I got one of those dishes that was designed to pick up the signals that are sent out from one place to another. And it was a microwave dish. That's what we call that signal. Just like your cell phone receives microwave signals. But these signals are not just going out in all directions. They're beamed from one place to another place. So you have a dish here and a dish here, and they're pointed at each other. And the cable TV signal I got, well, think about it. The cable station, they have to get their signals from somebody else. Okay? And their signals came from a big satellite dish that was located across town. And then it was relayed, it was bounced off another dish to the cable company. So they had, this one got it from the satellites, and then they had another dish that sent it across town to the cable company, right? Then they send it down the wires to your house, and they do all this stuff to it so you can't steal the signal, right? Well, it's perfectly legal for you to intercept anything off of the air. They can't control that. So I had my own little satellite dish here, my own little microwave dish. It wasn't pointed at the sky, it was pointed at the signal that they were getting. Okay? So I got it before they got it, and before they passed it on the cable and charged us money for it. You can't do that anymore, but you could then.
So how did you know where they're
Well, it took a while playing around with it. I had to fuss with it a lot until I picked up the signal. And the reception wasn't the greatest because I didn't have a big dish to pick up their signal with. But it did work. It was kind of fun while it lasted. And it was legal because it was coming off the air. Now, if I had cut into the neighbor's cable TV wire and got my signals that way, that would have been highly illegal because I'm stealing it directly from the cable company. As it was, I was only taking it off the air. So anyway, Electromagnetic energy. Remember that the longer the wave we're trying to pick up, the longer the antenna. Which has a longer wave, AM or FM? AM. Which has a longer wave, FM or microwave? FM. Okay? And that's why the antennas, AM antenna would be very long wire wrapped up in the coil. FM about 2-3 meters, if even. Your microwave antenna is very short. Okay? It might be like that long. If it's not sticking out of the phone, it might be built inside and be only 6 centimeters long or something like that. So we get smaller antennas as we get shorter wavelengths. Next. Ground. You know that as a ground connection. I also want you to know it as a common connection. Ground connections are there for a number of reasons, one of them being safety. If wires were to short out and live wires were to touch the metal casing of the lights there and I touched it, hopefully I wouldn't get electrocuted. Hopefully the electricity would flow through the ground wire all the way into the earth and it would go that way instead of going into me. That's why these wall plates are grounded, because there's electricity right there. If wires were to come loose and touch that, and then I touch the plate, I get shocked. And I don't mean just, ooh, it hurts shock. I mean, ooh, I'm dead shock. So by taking that wire and connecting it into the earth, we have a ground connection. You guys know where your breaker box is at your house? Where you can turn off electricity? You should all know that. Just like you should all have a fire plan if your house catches fire. You should know where the breaker box is. So if somebody's getting electrocuted, you can run out there and you can flip off the big switch and save their life. Well, right by that breaker box, if you look down around the ground, you might see a wire coming out of the house or even out of the ground, and it might be clamped on, a bare wire might be clamped on to like your metal water pipe that goes into the ground. That's the ground connection for your house. Okay? But we also use that symbol, like you see here on this schematic, as a way of indicating that these all have a common connection. I could just draw a line straight across here. And you may say, well, why not just do that? Well, because then I also have to draw a line up to this one, and this one, and this one, and this one. By using that symbol, I'm saying that all these points are connected together. That's connected to that, which is connected to that, and so on. That's why it's called a common connection. Yes?
Like in the outlet, I was at my home's cabin, and we're putting outlets in, just like the cover on.
Mm-hmm.
And I accidentally touched like this copper piece, when you're putting it on, I touched shock like really bad. I fell back.
A copper piece. Do you mean a bare copper wire in there?
Yeah.
Well, you must have been touching another hot wire then too.
Well, because I didn't feel like badly shocked.
A ground wire should never shock you unless you're touching something else. You might not have even realized it. Maybe one of the wires was plugged into the switch and you were touching another point on there, another connection on there. What often happens when people get electrocuted is it's just carelessness. They may be people that work with electricity all the time. I know that when you work on TVs, there's high voltage. And you're trying to be real careful not to touch certain things, but your pinky's out. You're grabbing something and your pinky's out and it's a little close to this, and it doesn't even have to touch in the case of a TV. Electricity can arc, can jump short distances because it's high voltage. And suddenly you see a little blue arc to your pinky, and it's like, ow, and it can really hurt because that's high voltage. Now, it's not as high in the outlet, but it's high current. And you can be close to something. You still have to touch, though. It's not going to arc in your regular outlet. Okay, next one. This one you recognize, we've covered this one, is diode. The diode was used in our crystal radio as the detector. Remember what it did? Remember how we had our positive and negative flow, and the diode cut off all the negative stuff? It opened the envelope, so to speak. It got rid of the garbage. Well, diodes are used quite frequently like a one-way gate. I described them to you before as those turnstiles you go through. Click, click, you go through and you can't go back. It's the Roach Motel. You check in, but you can't check out. You can only flow in one direction. And they often, well, they should have a label on it like that, plus. So you know which one goes to the plus side and which one goes to the minus side. Diodes don't all look the same. There are many different kinds of diodes. Now, this is one of our semiconductors. We're getting into semiconductors now. They kind of sort of conduct. We can control the flow with a diode. We can control, in this case, making it go one direction. So they're often made of that black stuff called silicon. Sometimes they're made out of other elements like germanium. That was the one that you had. That glassy one that you had on the crystal radio, that was their germanium diode. And you'll notice that whether they're clear, that black silicon, reddish, whatever, they have numbers on them, almost always, and they have a band, a single band, not like the resistors that had a whole bunch of bands. They have a single band. That band tells you which way to put it in. If you put it in the other way, it's going to prevent it from flowing the way it's supposed to go, and it's going to keep it from working. So, for a diode, again, what you're looking for, the telltale signs are that it may be this black material, it may not be, but it will have some indication about which one's positive and which one's negative. Usually have numbers. These are more typical of diodes. See that you can start to see a little number there, a little 5. You can see the one band. Tell me which way to put it in. On these, though, there is no colored band. So how do I know which way to put it in?
Yes.
No. Do you see any differences there?
Oh, like that side's more rounded off.
Yeah, the right side is tapered. It's kind of rounded off to go with the schematic symbol. So I know which way to put it in. Okay? By the way, we had talked about a device before. For a star, who can tell me the name of the device that turns AC into DC? That's the only thing it does. Devin? No, this is something found inside the AC adapter. AC adapters includes something else as well as this. The thing that turns AC to DC. I told you it was basically 4 of these diodes in a package. It fixes the situation. Say it again. Close enough. Rectifier. A rectifier is 4 diodes working together. And when you do that, then you're able to not just cut off the bottom, you're able to flip it over. Turn the negative into positives. So you can see this little guy here, it's pretty handy. This has 4 diodes inside it. You hook up AC here, and you get a plus and a minus there. It's not exactly like DC. It goes up, 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 up in a whole bunch of mounds, okay? But it does turn AC into a kind of DC that will work for our purposes. A AC adapter, as you mentioned, has this and what other part? This changes it from AC to DC. What part changes the voltage? Sky? Transformer, that's right. Okay, and we'll get to that in a second. So those are diodes. Next. Looks like a diode. Still really is a diode, but it's a special diode, a LED. Light emitting diode. Emitting means to give off. And this diode, when it lets electricity flow in one direction, and it does have a plus sign on it as well, it also gives off light. If you're using one of these LEDs, light emitting diodes, for your quiz board, you've probably already discovered that they don't work if you hook them up backwards. They have to be hooked up one way. Not true for light bulbs. And LEDs are super uber cool. They come in all different shapes and colors and sizes. They use big clusters of LEDs like this now to replace traffic lights because they last longer, they don't give off all the heat, they don't use as much electricity, and they have very controlled light. Yes?
Don't they make like really
Yes, they do. And that's a new technology. We have LCD TVs and like LCD monitors and plasma TVs, but they're now coming out with what are called OLEDs, which is organic light-emitting diode TVs, and they're some of the better ones. But anyway, they come in all different colors. They give a nice pure light, and until recently, it wasn't possible to have a blue or a white one. Those were huge advances. And before that, the big advance in LED technology was this kind of LED, laser light LED. I made a laser out of high school, about 21 years old. My friend and I, we decided we were going to go try to make a laser. And we got plans for one, and we built this big plexiglass box, and we ran nitrogen gas through it. And these are called solid state lights. They don't have any little filament that's going to break. Okay, they're very durable and dependable. Ours was not a solid state laser. It's the way they make the highest powered lasers. But even if we had been successful, our laser still probably wouldn't have been much more powerful than this one. Might have gotten a little hot on your hand, but not very hot. To be able to make lasers like this, an LED, okay, they don't look red like that, by the way. They look clear if you look at it directly. When it's off, they're clear. But to make a laser in the form of an LED is amazing to me. It cost us $300 in materials, and it's hard to find someone to sell us a canister of nitrogen for obvious reasons, but finally we did get some. You can imagine how shocked I was when I saw that we could now make laser light. We could get laser pointers like this for $3-5 even. That just blows my mind. And this kind of light, this laser light, this pure, intense light that can be focused on a tiny little spot is what made CD players possible. That's how we're able to read CDs. And then what led to DVD players and now DVD burners. You're able to use that light to focus on a spot on the disc, intense heat, to actually change some dye that's been put on the disc, to burn little pits into the disc and make your own disc. And you guys just take it for granted. I still look at that and I'm like amazed that we can do that and do it so cheaply. Zach?
How come it's so difficult to make white and blue ones?
How it's so difficult to make light what?
White and blue LEDs.
I'd have to have a higher degree in physics to be able to answer that question. It has to do with the wavelength, and the most common is red. Most common kind of laser light is red. This is the cheapest to manufacture. After that is green light, and you could get a green LED laser pointer for about $150. It is about 10 times as bright and goes a lot farther. You can use it to point at stars in the sky so people can see what star you're trying to point at. And then after that, I don't know why. I think it's the wavelength that makes it more difficult. Yes?
Are LED lights the ones that are like the spiral lights?
No, those are fluorescent, compact fluorescent. But those are also a good green solution. They save a lot of money. Nathan?
And my friend on eBay bought a $500 laser, and it's green, and he can like point all the way to his friends' houses and stuff.
Oh, I'll bet. I'll bet. Can you bring it in? Well, you wouldn't be allowed to have it at school, but if you brought it before school, I'd love to show people that as an example between the difference. I've wanted to buy one of those because I think they're really neat. Yeah?
Can you just put like a green LED light in there?
No. This is not laser light. There's something different about the light and how it, I don't want to get too technical, but the way the light is focused. It's not just a green LED inside there with a big lens focusing it. There's something unique about laser light that causes it to travel in these parallel lines instead of going off. See, this will give off light in all directions. Boom, 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 in all directions. Okay? Whereas laser light, I can do this and you don't see light coming off this way or this way. It stays all parallel and even. That's what's unique about the laser light and lets us focus it.
Is that why mirrors like reflect it? Because it's just like a focus
Right.
light?
Boom, boom, straight off. Yes.
Well, do they ever make a laser that heats up?
Did you say mirrors don't reflect it?
No, it's in mirrors.
Oh, okay. Oh, yeah. This would heat up. if left on. You might even feel it on yourself if you leave it on the same spot long enough. But if we increase the intensity, it uses more watts. It's going to give us more intense light. And that's the kind of lasers that they use in dermatology and other treatments of cancer. You know, they can get in and they can focus. I want to not damage the skin here, but I want to kill the cancer down here. I can beam that and focus the light so it aims at that point, and it doesn't damage the tissues up here. That's pretty cool. Okay. Now we're on to light bulb. I'm going to kind of pick up the pace because most of these are reviewed that we've covered already. Light produces light and heat. The goal is not to get heat, but a light bulb's not very efficient. An LED is much more efficient. Better way of getting light. And they now have clusters of LEDs in a little socket thing you can put in your lights at home. They may cost you $30, but they produce light with very little heat, and they waste a lot less energy. Then we go on to speaker. You know how a speaker works. I already went through that. It's basically an electromagnet that moves a piece of paper or a piece of plastic back and forth. Converts electricity to sound. We've got our voice coil. We got our permanent magnet that it's pushing and pulling to and away from. And then we've got our attached diaphragm. That's the piece of paper or plastic. The headphones are the same as the speaker. Electromagnets converting sound, electricity to sound. You just put it on a strap. Headphones are electromagnets that convert electricity to sound. Just two of them on a strap. Don't put the headphones on the baby and play Metallica. Okay? They only have so many of those little hair cells. You don't want to destroy their hearing when they're only 9 months old. Next, this is probably the single most important technological development of the last 1,000 years, in my opinion. You heard about the inventor yesterday, William Shockley, invented the... Nobody remembers, huh? Starts with a T.
Television.
No. That was Philo Farnsworth. Transistor. Transistor, okay? Transistors you will know by their 3 wires. You can see it on the symbol. 1, 2, 3. They are often made of that black silicon because there's something that we call a semiconductor. And they have 3 wires. They can be used to switch. They can be used to amplify. You can do a variety of things. Those are 2 of the common functions. See how we can control what flows through, which way it flows. The 3 connections are emitter, base, and collector. You don't need to know that, but how you hook this up is very important. Those 3 wires, they have to go in a certain way. Before transistors were available, before these little guys were available, the part that did that same job in the 40s and 50s was the vacuum tube. The vacuum tube was much bigger, much less reliable, used a lot of electricity and gave you a lot of heat. Computers were huge, had to take up football fields because they had bank after bank, row after row of vacuum tubes. And they needed fans to keep them cool. The transistor comes in and much, much smaller. This was like some of the early transistors. Much smaller. I mean, this is the early transistor. This was the early vacuum tube. Okay, hundreds of times smaller. Much, much smaller. And more reliable. And then scale them down further. This is a common transistor size. You can see the 3 wires. One of them's broken off, or 2 of them broken off there, but you can see where the 3 go. And they're often little half-moon shapes like that. But they always have the 3 wires. This is a power transistor. That little piece of metal takes away some of the heat. They always have 3 wires. And we took it a step further. In the last 25, 30 years, we went from just having transistors to being able to miniaturize those, to be able to make one like that, but microscopic. You wouldn't be able to see without a microscope. We could actually carve it into silicon. Okay, and that's going to lead us to our next one. The next one is this guy right here. That's not just one kind of part. It's actually combinations of these in one little package. What's it called? Integrated circuit. To integrate means to put together. And if we take little miniature transistors, resistors, capacitors, we build them on a microscopic level out of silicon, that black stuff, we now can make a calculator on a chip. We can make an amplifier on a chip, a cell phone on a single chip. We can build all these things in miniature form. And being able to miniaturize all this means that if the transistor's smaller, it's going to need less electricity. We can get the same job done with a lot less current. Laptop computers, cell phones, all these little small portable electronic devices, they're possible now because of these. One of the reasons your cell phone is so much smaller is because of the chip. Also, is when we made the chip smaller, the electronics smaller, we took all of this and we squeezed it down to a little tiny integrated circuit. We also reduced the amount of electricity needed. And so the battery got smaller too. So all of our electronics have gotten much smaller. You know, I told you about the cell phone that we used to sell at Radio Shack that was this big and weighed about 10 pounds. And you had to carry it like this and it had a regular wired handset that you would use. Your phone is far better than that and would last a lot longer than that phone because we got all the parts miniaturized and the battery miniaturized. Okay? I'll show you some examples of ICs. This is an integrated circuit. You guys know it as the CPU, the main brain in the computer. Within this space is a little chip, a little IC that has, and I'm not joking about this, millions of those. Millions of transistors in microscopic form and other parts in microscopic form. Head up, Andrew. We actually, they make it using, I'm not exactly sure what the technology is, but they do it in clean rooms and they use little microscopes and it's all automated by computer. But basically, they can draw it out, a physical drawing of what it's supposed to look like. And that drawing then is, they use photographic methods to shrink it down and treat silicon so that they can get rid of the stuff they don't want and keep the stuff they do want. And they can make it like that. Boom, boom, boom. They can crank out these chips super fast. And that's how we're able to get memory chips and computers as cheaply as we are. These have, you know, more labor and materials and time involved in them, so that main chip on the computer might constitute, you know, $300, $200 worth of the cost. The rest is all the other parts. Okay, but we have chips in all different sizes. Here's an IC that is a keyboard controller. When you hit a certain key, Q, this sends out a certain code to the brain. Okay, here's another one from some Apple computer, and they come in all different sizes. I even have, oops, somebody must have liked that one. I'm missing one. A lot of good it's going to do them. Well, I had a, oh, there it is, it's stuck to the bottom. This one right here. This is a car stereo amplifier. I can tell you what these things are. That one I know because I took it out. But I can tell you what some of these are by reading off the numbers and checking them up. But the other thing I want to show you about these ICs, regardless of the size, they do have some things in common. You'll notice that many of them have notches on one end. See that notch? This one has a notch as well as a little divot. A divot in golf is when you swing the club and you hit too deeply and you hit the ground instead of the ball, which is what I do. You know, the ball goes backwards and the grass goes forward and you hit the grass farther than you did the ball. Well, what you're supposed to do is go pick up that clump of grass and stick it back in the hole so that you don't ruin the golf course. Okay? They call it replacing your divots. Well, there's the divot on that one. You see it? A little dimple, little depression right there in the corner. Well, those two things are your indication about what what number each of these connections are. These connections are called pins or legs, and some of them have a whole bunch of them. And when you use these in a circuit, when you add these to other parts, like I have on this one, oops. When I do that, I need to make sure that pin number 1 is hooked up to the right place and pin number 8 is hooked to the right place. So if it has a little dimple, that dimple will always mark pin number 1. If it has a notch like this one does, the notch will tell you that the pin directly below it is pin number 1. Then all we got to do is, once you know what pin number 1 is just read across from there. So if this is the divot, this is pin 1, goes 2, 3, 4, then we skip to the other side, 5, 6, 7, 8. Get it? And that works no matter how many pins it has. Like this is the divot, 1, 2, 3, 4, 5, 6, 7. What's that one? 14. What's that one? 8. Okay? I do need you to remember how to do that because we're going to need to remember that when we build our own. But every IC has pins or legs like that, connections like that. Sometimes they give us a little socket so that we can take it and we can stick it in the socket. If that part goes bad, it's nice because we can pry it out and just pop in a new one. You can do that with these processors for some of your computers. If it's outdated, you can pull out the old processor, plug in a new one, and upgrade your computer that way. All right, this you know is coil. Coils convert electricity to magnetism or magnetism to electricity. It just depends on which way we're using it. If we're hooking electricity up to it, we're trying to make magnetism. If we're using it with a permanent magnet, we're trying to make electricity. There's just a plain old coil like you might get out of some electronic device. There's another one that's been commercially manufactured. And you know that if you take two coils and you put them side by side, you have transformer. Those little lines in between indicate metal plates. You can see on this transformer here, this big clunky part around the outside, it's metal plates. Those plates separate the two coils, and they help that magnetism be passed on even better. So you'll see often with these transformers, whether they're big or small, that they have this piece that goes around and kind of divides it in half. And usually they're wrapped in tape, so if you take that tape off, you would see your coils of wire underneath that. Sometimes transformers have 4 wires, that's the most common. 2 for the primary, 2 for the secondary. Sometimes they have more than that. They have multiple taps. That's for other things that we won't get into, okay? But you can recognize them by that basic shape, that piece that goes around. They're going to change the voltage. They're not going to change it from AC to DC. That's the rectifier that does that. Next we have battery. Won't spend much time on that. You guys already have a definition for a battery. You know it's going to have one side labeled positive. It's going to have one shorter than the other. This is telling us that the two electrodes are different. That's going to pump out electrons through a chemical reaction. Our last part comes in so many varieties that I could show you 100 of them and still wouldn't cover all of them. These two symbols are both examples of switches. This is a simple switch, an on-off switch. This one would be a push-button switch. And like I said, depending on how many things we're switching, the switch is going to look different, and the schematic symbol might look different. Here's a simple on-off switch, a flip switch. Okay? Then we go to push-button switches. This is called a momentary push button. You would use that symbol for it. It's only on as long as we hold it down, like a doorbell. Here's another momentary. Okay? You can tell they're switches because they got something that clicks back and forth. This is a rocker switch, has 6 connections on the back. This is a slide switch, has 6 connections on the back. This is a single pole double throw switch, they call it. It has an off and 2 on positions. You could use this if you're using a motor. Forward, off, reverse, off. Has 3 connections on it. This switch has a bajillion connections on it and has a bunch of different positions. It looks a lot like the variable resistor, but it clicks. So we know that it has a bunch of different on positions. It can switch a bunch of different things on or off. These guys are switches, and yet there's nothing that you control with your hand. These are switches that are controlled by electricity. And these are called relays. And you've heard a relay before. Every time you turn on the turn signal and you hear click, 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 that's a relay. The way a relay works is instead of using your fingers to flip a switch, you use electricity to flip the switch. When electricity goes to this silver coil, it pulls down this metal plate until it touches the little round plate. When those two touch, you create a circuit. And you did it by sending it electricity. Okay? Now, I did promise that I would show you the Van de Graaff generator using my capacitors. These are 2 jumbo-sized capacitors over here. And what's actually going to happen here is I'm going to charge up these capacitors, just like you charge up the capacitor in your camera flash. And when it builds up, the charge, I won't get shocked this time, the charge, it'll store a much better charge than we did, our bodies did. And I'm actually like filling up those jars with electrons. The inside is covered with foil, the outside is covered with foil. And the electrons want to get from the inside to the outside. All you have to do is provide a path. You hear that high pitch? That's high voltage.
No.
Okay? Anyone want to try it?
Wait, what do you
No? Come on up.
Do it.
I'll do it.
Oh my god.
Put your hand down like this on the copper plate with your thumb up. Hold on, we want to see it. Put your hand down there. Quick, quick, quick.
Hurry up.
Quick, quick. No, with your thumb up. Hand down, thumb up.
Oh.